Okay. Have you ever seen those boba teas that everybody's been into lately? Well, take a one of those straws that come out of them. They're the really big, wide straw. All right. And take a deep breath through one of those, like a wide tube through that. It'll probably be a lot easier than taking a breath through a coffee stir. Same lung, same effort for you, and suddenly it's exhausting. And here's the thing. The straw isn't a little narrower, but it isn't a little harder either. It's dramatically harder. And by the end of this video, you'll know exactly why the math is so brutal. Start with this. Gas doesn't always move the same way. There are three patterns. Laminar flow is smooth. Gas moves in concentric cylindrical layers. Fastest right down the center, slowest along the outside walls where it drags. Turbulent flow is chaotic, swirling, disorganized, no orderly layers at all. It takes a significantly more pressure to push that same amount of gas. And density is the property that matters here. Transitional flow is a mixture of both of them, and you'll find it wherever airways branch, at the carana, at the bronchial bifurcations. And here's what to remember about a real patient: the tracheobronchial tree branches constantly, so most of what's happening in there is transitional. So, what tips a smooth flow into chaos? Four things. You have high velocity. Fast moving gas loses its orderly pattern. And this is why a patient in distress breathing hard and fast makes their own resistance worse. Large central airways. Turbulence is more common in the trachea and the mainstem bronchi than out in the small peripheral airways. Irregular surfaces, so secretions, a tumor, a foreign body, an inflamed airway wall, anything that disrupts the streamlines. High gas density. So denser gas mixtures tumble into turbulence more readily than lighter ones like heliox. So why do you care? Because turbulence significantly increases the work of breathing. Your patient is spending a lot of energy just to move air, and every one of those four factors is something you can change sometimes. Which brings us to Posey's law, which puts numbers behind all of this. One caution before we start. It describes flow through a straight, rigid tube under ideal laminar conditions. Airways are none of those things. So we use it to predict direction and magnitude and not to compute exact patient values or anything. For relationships, watch which ones affect flow and which ones affect resistance. So we increase the pressure gradient and flow increases, resistance hasn't changed. You're just pushing harder. And that's what a ventilator does. Increase the length of a tube and resistance goes up. So flow drops for the same pressure. Longer circuits give you more drag. Increase the viscosity and resistance goes up. So if there's thicker fluid, it's harder to move. And increase the radius and flow increases dramatically, not proportionally, dramatically, which is the whole next slide here. Before I show you, let's stop and think. And I want you to write your answer down. If airway radius is reduced by half, right? Does resistance merely double or does it change much more dramatically? Resistance is inversely related to the radius raised to the fourth power. So if you half the radius and you don't double resistance, you increase it 16-fold. A tiny change in airway size produces an enormous change in resistance. So that's back to our first example of the coffee stirrer. And that's also why a toddler with a little airway swelling is in serious trouble, but an adult with the same millimeter of swelling may not even notice it. Clinically, this cuts both ways. bronchospasms, mucus plugging, and airway edema all reduce radius and resistance skyrockets. Bronchodilators actually increase airway radius, reducing resistance. So, when I say bronchodilators, that's like a albuterol or inhaler. The Reynolds number bundles those turbulence factors into one concept, and you don't need to calculate it for week one. And I'm not going to give like a full cutoff number. I just want you to know which direction each factor pushes here. So if the Reynolds number goes up, meaning turbulence is more likely with higher velocity, larger tube radius, and higher gas density, it goes down with higher viscosity. A larger radius makes turbulence more likely. A smaller radius makes resistance higher. Both of those are true. They're answering different questions. One is about flow pattern and the other is about opposition to the flow. And heliox shows up here again. So lower density lowers the Reynolds number, which favors laminar flow. Two related ideas, and they're easier in this order. Continuity first. If the same volume of gas per unit of time has to get through a tube and the tube narrows, the gas has no choice but to speed up. So squeeze the path, velocity rises. Bernoulli second. As gas speeds up, it pushes less on the sides of the tube. Its energy gets redirected forward instead of sideways. So faster gas means lower lateral wall pressure. The Venturi principle takes Bernoulli and builds a device out of it. So we push pure oxygen through a small orifice, velocity jumps. Lateral pressure around that jet drops. And now you have a zone of low pressure sitting right next to room air at atmospheric pressure, which means room air gets pulled in or entrained. And this happens through side ports built into the device. That's the mechanism behind air entrainment masks and jet nebulizers. Source oxygen plus entrainment room air mixing to deliver a specific FiO2. But that intended FiO2 only holds under two conditions. The entrainment ports have to stay open and the mixing changes. And total device flow has to meet the patient's inspiratory demand. If your patient is pulling harder than the device can deliver, they make up the difference with room air you didn't account for. The calculations behind all of this, air to oxygen ratios and total flow, those are week 3. Today, own the mechanism. So I know this is probably a little tough, but we'll work on this more in class. The thing is to open your textbooks and take a look at some of this stuff. 5 things I want you to carry forward from this. 1, flow always moves from high to low. Every breath and every device exploits a pressure gradient. Number 2, radius is king for resistance, the 4th power rule, right? So the smaller the radius gets, the dramatic increase in resistance that you may find. Number 3, density belongs to turbulent flow, viscosity to laminar flow. And number 4, Bernoulli plus Venturi equals air entrainment. And then 5, the gas laws. Boyle's Charles Dalton govern how devices behave. Every respiratory device manipulates pressure, flow, volume, or resistance. So, the clinical challenge. Adequate source pressure does not guarantee adequate patient flow. You now have the checklist. Is the pressure gradient sufficient downstream? Is the tubing kink, narrow, disconnected, or obstructed? Has resistance increased? Is flow turbulent, or is the device assembled correctly? I'm giving you the checklist, not the answer. Bring your guided notes and a calculator with you, and we'll work on actual cases together in class.